Hi, my name is Michael Champlin, and today I am presenting to you computational thinking, literature review, and proposal for a high school algebra classroom. All right. So, introduction is first off, let's talk about computational thinking. So, CT or computational thinking focuses on the parallel processes of computers with the brain. So, in other words, we like to think that the brain thinks like a computer, right? You have a bunch of neurons that scatter and connect to help you retrieve memory and thoughts and reprocess your knowledge, all right? And computational thinking is a process of critical thinking, problem solving, and a tool utilization. Okay, we'll go into further into that. Further, this project focuses on an investigation of the importance of computational thinking in a math classroom, specifically algebra. And we're going to analyze computational contradictions, people's contradictions, and provide resolutions and strategies using high school algebra curriculum or concepts. So, for a little background, uh, computational thinking is fairly recent. If you look in growth of education, it started with Seymour Papert. Hopefully, I said that right. Who introduced it in the 1980s, early 1980s, like 1980. Uh, but he proposed it as a form of computer science. So the focus was more that the brain, yeah, it still is a thinking process similar to uh, technology, but the focus was including it into computer science. Whereas Jeanette Wing realized, hey, we can use this for all sorts of subjects and it'll be super beneficial for a learning process. So in 2006, Wing presented, hey, let's start applying this to all school and academic processes. Again, background, the process is a lot like computer data processing. The brain can cognitively decompose new information, analyze it, categorize it, and make connections. Um, by doing that, we can come up with our outputs and come up with some knowledge that is pretty impressive. Very similar to the way computer works or digital programs work. And we also, with computational thinking, we like to utilize tools to help us retrieve memories and help us store knowledge and record information. So, yeah. So we also use some additional support systems or resources. To continue a little bit, let's look a little deeper into the critical thinking, problem solving, and tool utilization. So, with critical thinking, that is the how-to process, right? How do we think about this? How do we acknowledge what's going on? So, example, like with algebra, we look at parabolas or quadratic functions, right? And we make connections that a parabola is a quadratic function, right? Because of its shape, of its equation, and what kind of roots it has, the vertex, the domain, um, and all those properties of a parabola that helps us identify to help us really in-depthly think about a quadratic function. As far as problem solving, this is where we kind of apply the mathematical knowledge and skills to discover a solution or discover new knowledge or to re-embrace or support prior knowledge. All right. So, for example, going back to analyzing a parabola, if you can identify exact coordinates, you can actually apply that parabola into real world effects. For example, look at Pringles, the chip, right? If you can discover a shape of a parabola, that actually makes an amazing potato chip shape. Um, Also beneficial is architectural construction, such as like bridges and just buildings, roofs, and trajectories, right? Like a missile launch, right? You can predict where it lands with you while analyzing a parabola. And finally, tool utilization. So whether it's digital or analog, these are tools that help avoid the tedious nature of some mathematical concepts, right? So like a graphing calculator or a coordinate system, blueprints, computer applications, or right down to a pen and paper, right? I mean, if you have to write something down, a number, so you don't have to memorize it, so you can go back and look to move on, that is totally tool utilization. All right, looking at the next. So the issue is there's some contradictions. First off, educationally innovating, it's new. CT is fairly new. Instruction, we need people who are invested, teachers and learners who are invested in the process, and tool appropriateness. So where's the moral or the ethics of using some of these tools? All right, to take a further depth looking at it. So again, this is a newer concept, right? It's been proposed in the early 1980s. So it's been roughly around for 40 years. And 20 of those years was focused primarily on computer science. So that being said, 20 years now, looking into it, means that it's young, right? Academia has been going on for centuries. So the fact that this concept is roughly 20 years old as a universal academic process, there is a lot of doubt that it's not fully developed yet. So that leads to the next topic is this. We don't have much research on this. It seems like we have it, and it's with the internet and stuff, it's becoming more growing, but yet we still don't have a lot to compare and contrast, right? So unfortunately, many scholars do argue that CT practices is not substantial yet. We don't have enough data. We need more data. We need more evidence. So whether it's positive or negative, we just need evidence. And further, we need people to take it serious. We need actual scholars and actual experimenters take this research seriously, computational thinking seriously. As far as instruction, again, we need teachers that are invested, and not even just new teachers. We need experienced teachers. We need people that are willing to take on a style. And I know this is difficult because some teachers have been using a specific style or traditional for decades, and it's hard to move to new techniques, right? So you might feel intimidated or uncomfortable, but yet we need some teachers that are invested, right? And committed. You can't just start incorporating CT practices and then just say, hey, I got to take a break, right? So unfortunately, you need full-on curricular cycles of implementation, right? We need teachers to do this for a couple of years so we can have analysis, so we can have good data to analyze and good evidence. And unfortunately, we have a low volume of volunteers right now for that. As far as students goes, teachers are very influential, right? If a teacher's not invested, a student's not going to be invested. So that is very important. So to gain respect from a student, a teacher must be invested too. And I know that some people are scared that if we implement computational thinking, so such as like the tools, students may lack adequate math skills. And further, we just came off COVID-19. So there already are students that are weak in certain math skills that we're already working on. So adding computational thinking to developing from a worldwide pandemic may seem scary. However, computational thinking has possibilities to actually improve that. Advanced tools. Let's be honest. The fact that these advanced tools can provide solutions does mean that students need to be honorable and responsible for it. So there is a concern that students may use these computational tools for cheating, right? Like they're just going to find the answers, and I get that concern. However, they have to have some sort of moral support to figure this out, and we need to not focus on losing academic trust, but how to properly train them and train these tools as a resource. And again, will these tools take away from the basic skills that these students may learn? No. If they are properly trained, we can move on from utilizing a tool versus using a tool to find an answer. So, resolutions. CT strategies with high school algebra, again, I'm looking at this as a perspective as an algebra teacher. So we're going to look at some examples, benefits, and proposals to incorporate to how to avoid these contradictions. So again, educationally innovating. It is new, okay, right? So what needs to be done is supporters of computational thinking really need to take the initiative of including CT in their curriculum and continuing to include their CT in the curriculum and providing evidence. They must keep evidence. So that means in algebra, we must spiral, space, scaffold assignments for such effects like in algebra, we have factoring, solving equations, function properties, and inequalities. There's so much stuff we can involve computational thinking in. And as far as evidence, our assessments, right? So first up, low risk assessments. Yeah, not everyone collects them, but if we're trying to prove a point, collect those low risk assessments, collect those homeworks, collect those warm ups, exit tickets, right? Just to gain that evidence is what we need. And then of course we have quizzes and tests, right? The overall knowledge and conceptualization of the students is very beneficial. Um, as far as algebra goes, an example would be great is solving equations, right? Like when we're evolving from one step to multi-step equations, this goes beyond using skills of PEMDAS, right? And your evidence could be showing the growth again of maybe students solving one-step equations and then solving multi-step equations with such things as like square roots and inverse operations. And always a unit test and a summative test is always great for comparing and providing evidence of the computational results. As far as instructions go, teachers have to say this over and over again. Teachers must be invested and committed, right? We need to see through a curricular cycle. You can't just give up and go back to different styles. You have to stick it out. And you will see once you start gaining mastery and using computational thinking that it becomes easier and more progressive with your material. It's very engaging and reflective too. And when you're modeling, present it positively, right? Let's gain that attention for students. Let's boost that energy. All right. I put in here an example as factoring polynomials. A good thing about computational thinking is struggling, right? Who doesn't have a student in math who doesn't struggle? There's some point. Well, a major one in algebra is students struggle with learning factoring, especially polynomials. So start off with something with modeling just simple digits, right? Like the number 8. Well, the factors are 2 times 2 times 2, so that's 2 cubed, right? And that can evolve through computational thinking tactics. You can evolve that to doing polynomials, converting binomials, pulling out the greatest common factor, or converting binomials to trinomials, or vice versa, right? So it's very resourceful in algebra. As far as advanced tools, this comes down to teacher modeling, right? Teach the appropriateness. If we show the students how to respect a tool or how to respect a computational tool as a resource, they can flourish their thoughts, right? Like, so if you're using a graphing calculator to help you graph a parabola, for example, or any function, you can identify by looking at it, by the shape. You can identify whether it is an absolute function or it is an exponential function, right? So yeah, maybe they're not going in and hand writing a function, but they're learning faster what different types of functions are, what the shapes of the functions are, how to process the coordinates and apply them to real world evidence. So there's just so much with the tools that can benefit them besides just getting solutions. So in conclusion, again, I believe that CT should be involved in all education. I think it's a growing process, and I think that critical thinking, problem solving, and utilizing tools is extremely beneficial, and technology is growing, so we should, as individuals, grow with the technology. Um, as I've said it multiple times now, computational thinking supporters should remain committed. Keep presenting positive interest, techniques, and evidence. And it's super resourceful in high school algebra. I mean, you can use digital and analog tools to break away from deeper understanding. You can critical thinking with, again, comparing functions, examining graphs, and problem solving. And again, problem solving goes way beyond finding a solution. Problem solving is understanding real life applications and incorporating ideas with across all academia. All right, so I hope this was resourceful for you, and I hope you have a wonderful day. Thank you very much. My name is Michael Champlin, and here are my resources.